Okay, so thank you for having me. Thanks to the organizers. It's a real pleasure to be here. And today I'm going to talk to you about categorical game theory. And so let's talk about talking about what games are. So game theory is a mathematical study of interaction among independent self-interested agents, which is a very broad definition, which embraces a lot of situations that we can put under the general umbrella of cybernetics in a sense. And this means that this area is very applicable in a sense. And so I want to have forward about what applications are to me. There's this quote by Tadashi Tokieda, which really speaks to my heart. He says that often mathematics is applied in very bad ways. And so often people think that applications are things that can make you really rich or really powerful. And I really hope that with the work we are doing, we could explore mathematics in a way which is actually going to do something for the good. We're very far from that, but hopefully improving mathematical facilities will also improve the tools that good people have to actually make progress in this direction. But anyway, let's talk about games again. In game theory, we have two classical ways to represent games, which are called normal and extensive form. We have normal form on the left. In normal form, a game is simply a utility function. So it's an assignment of rewards to every player, given a set of actions that they actually enacted. So there's very little information in this description because we don't know what happened in the game, which is new. Players made some decisions, but we have no idea how the game actually was played. Extensive form is a little bit better from this standpoint because we have a tree which represents, in a sense, the history of the game. So every node is a state of the game, and every time players can decide which branch to take. And at the end of the day, we reach leaves where payoffs are. So everyone gets their own reward. The problem here that this is a really big representation. So we have too much information here. We have like a branch for every move. So imagine a game like chess, you have 40 moves for every round. In a bunch of rounds, your tree is already bigger than the universe, so it's not really useful. And most importantly for us, this is not compositional. So this is good for small situations like those kind of thought experiments that game theorists love a lot, but not really for large scale situations like economic games. So we need something which is more compositional, and that's where open games enter. This is a compositional categorical framework to do game theory, which was introduced by Hedges, Ghani, Winchell, and Zahn, I think 5 years ago. And it's based on representing games with string diagrams. And this greatly improved the situation because, first of all, this is a compositional framework, so we can actually hope to represent big situations and to, in a sense, tame complexity by using the language of diagrammatic of diagrams. Okay, so let's see. We want to translate, of course, from the classic representation to the new one. With normal form games, this is very easy because it's just a utility function, so it's not really interesting. But I'm sorry, this is so hard. But translating extensive form games is a bit more complicated because we have a big problem with agency. So we need to seriously consider how players actually intervene in the game. And this was kind of winged so far, but to properly translate extensive form games, we need to actually embody this in a proper way. And we need like compositional operators which are adapt to do this, this job. So we are going to introduce in this talk a framework called Open Games with Agency, which builds on the previous framework of open games and adds indeed agency, so players to the picture. And it's widely inspired and has inspired the cybernetic framework that Jules talked about on Monday. And we're going to see also new choice operators that will help us to actually make this translation happen. So let's look at this open games with agency. So again, we had this definition of games, and we see there are like two very important parts. The first is interaction. The second is agents. So we can figure a game as composed by these two components. One is what I will use green to represent, which is the game and how we think about it. So there's some mechanics, there are rules, things that happen, and agents are sort of hovering over this arena and make decisions and intervene in the game at different points and preserve kind of an identity. So players will intervene in the arena by making decisions at different points, and the policy they use to make these decisions is called a strategy. So each player will use a strategy to actually play the game. And if we put together a strategy for every player, then we get a vector of strategy we call a strategy profile. So let's look at the components now. An arena is going to be represented by this diagram, which is a parameterized lens. You might recognize a similarity with the diagram that Bruno showed us. And so we see there are three boundaries. On the left, we have what we call the state coming in together with a strategy profile coming from above. And there is a function we call the play function that uses indeed the policy provided by the agents to react to the state of the game and decide to make a move. And then later we have what we call the backward pass, in which a utility arises and the co-play function decides how to propagate this to the rest of the game, and most importantly, how to give back this utility to the actual agents. Okay, and so together this forms a parameterized lens, as I said. And if we add two a state and a co-state, so these big triangles, we get what we call a closed arena. And on the left, we have an initial state, which is going to be just a choice of an X. And on the right, we have a K, which is a utility function, which takes in a move and decides what value we assign to that move. On the other hand, and what happens when we close an arena, then we see that the whole arena and players turn into this picture, and we see that a closed arena amounts to having an evaluation of strategies with rewards. So from the perspective of agents, playing a closed game is like making a decision and getting back a reward for that decision. So on the other hand, we have players, and players, as I anticipated, are a distinct part of a game, which has a preference on the state of the world. And this is expressed by a selection function. So you see, we have a selection function is nothing but a thing that for each utility function, so an evaluation of strategies with rewards, assigns a set of strategies that the players consider optimal in some way. So the strategies they prefer to play. And the thing you should have in mind while looking at this is argmax. So argmax is the archetypal example of a selection function where players simply chose the strategies that maximize their payoff. And we can use selection function to talk about Nash equilibria, as we'll see later. But what is a Nash equilibrium in the first place? So Nash equilibrium is a strategy profile, so a choice of strategies for every player, which is such that no player wants to change their own strategies, given the fact that all the other players will keep their strategies. Okay, so no player has incentive to unilaterally deviate and change strategy. Okay, so we should imagine this as sort of a standoff. Okay, I can't move because I don't know what the other player is going to do, and the only thing I can do is change my own state because the other players, I don't know what they're going to do. Okay, so we are competing, and there's no way for us to agree on a multilateral change of strategy. We can model Nash equilibria using the framework selection functions by observing that the assignment of the set of selection functions on a pair of sets is functorial on lenses. And this functor admits a left monodal structure that we call the Nash product, which takes a selection function on a strategy and a reward pair, and on a strategy and a reward pair, and puts them together in such a way that we can model the situation that Nash equilibrium describes. So the product of selection functions will choose those pair of profiles, those profiles of those pair of strategies, so that no agent wants to unilaterally deviate. So if we have a game with n players, then and each has a preference, so a selection function epsilon I, then the product of all this selection function will have this type signature. So we'll see that on the left we have strategy profiles, which and reward vectors, and this function which is going to be fed to the product is a utility function, which is then given by a closed arena, and the product selection will therefore select a set of strategy profiles, which is going to be the Nash equilibrium of the game. So putting everything together, we see that we have the definition. An open game with agency is nothing but a pair of a parameterized lens and a selection function on the parameters. Okay, so the parameterized lens part is the arena, which represents the mechanic of the game, and the selection function represents the preference so of the agents which actually participate in the game. And the equilibrium predicate that we have in classical theory of open games can be recovered by evaluating the selection function on a given closure of the arena A. Moreover, we can say that a given game has a set of players P if omega and comega are presented as products over a certain set of players P. Okay, so we interpret every omega P to be the set of strategies for the player P, and omega P to be the set of rewards for that player. And of course, we need also the composition of the selection function. Okay, so we see that the equilibrium predicate is what we've seen in the previous slide. Now, composition open games means that we have composition operators, and the most important are sequential and parallel composition, in which games are played one after the other or in parallel indeed. And these are operators on games, so every time we compose sequentially or parallelly two arenas, we can also compose the assigned selections using the Nash product, okay? Because as you see, every time we compose either sequentially or parallelly, strategies and rewards get tensored together, okay? So we can also tensor the selection functions. On the other hand, we have to introduce two new operators, which are external and internal choice, which model a situation in which players or the environment can choose if they want to play a game A or a game B, okay? A1 or A2 in this case. So external choice means that the environment chooses for the player. So the players will receive a state, which is either a state for game 1 or a state for game 2, and they have to be prepared to play both, but they're only going to play one. On the other hand, internal choice means that the environment provides a state for both games, and the players will decide if they want to play game 1 or game 2. And these two operators, contrary to the other two we've seen before, cannot be extended to games in a canonical way. So there's no way to combine preferences of these choice games without making an arbitrary choice. And so future work will see if this is actually true, or we can refine our definitions to actually do this extension. But maybe the most important novelty in this framework is having reparameterization. So Bruno was talking about this before. Parameterized lenses have a second dimension, which I represent in blue in my drawings, in which we can also have lenses, which means that in a certain sense, there is also a dynamic happening between players. Okay, so everything we do in the blue direction means has a representation in terms of things that happen between agents. It's not necessarily tied to what happens in the game. For example, in the paper, we describe how a voting system between agents can be used, can be represented in this way. It can be used, for example, to assign a selection function when players have internal choice. But most importantly, we see that reward distribution and observational constraints, which allows us to implement imperfect information, will be useful later for the translation. So let me give you two examples of reparameterization. One is really important from a technical standpoint because it allows us to keep track of players across composition of the game. So if we have two games and they both have a set of players, we want to be able to identify when we compose them which players are like the same in the two games, okay? And we call this operation regrouping. And in practical terms, let's say if you have a game A1, A2 with 2 players, then we want to say, well, actually we have just one strategy profile set for player 1 and one strategy profile for player 2, and same for rewards. And these are going to be distributed in the 2 games. So the distribution is just a permutation, which we build like so. And then this tangle of wires is just a permutation, and this constitutes, I'm missing a slide. Well, this tangle of wires constitutes the thing I called regrouping before. The second very important instance of reparameterization is time. So time is a way to enforce the same strategy to be played at different points of the game. So instead of having, if we have 2 games, instead of having a wire for one game and a wire for another, we have just a single wire, and we use a copy to make sure that the 2 wires that are going into the game are going to be the same. And a very important application for this is to implement repeated games in which players have to play the same strategy at every round. And a little interesting fact, if we reparameterize along a copy, so along a time, then we get strictly outside the image of any composition operator. And this testifies that agents are really a new introduction to the compositional framework of games, which testifies some kind of long-range correlation, which wasn't expressible before. What I say is agency is non-local. But anyway, let's talk about now extensive form games, and let's see how we can translate from them to open games. So just to set down some notation, extensive form is an object like this. This is representing a game. We see that these are 3 nodes are states of the game, and each is assigned to a player, which is like has the job to actually decide a branch at that point of the game. And moves are branches. So every time we have to make a choice, we have different branches. And at the end of the tree, we find leaves, and these leaves have payoffs on them. So when the game ends, players get their own payoff from there. So this can be represented as a data type, so an inductive type, which is remindful of the type of a tree. Okay, so it's basically a decoration of a tree. So leaves are now decorated with a payoff vector, and nodes are decorated with a player, a number which says how many branches we have, and finally a function which gives us the subtrees at that level. Okay, so to recover strategies from an extensive form tree, we can write an inductive function, given the fact that our data structure is inductive. And a strategy for an extensive form game is simply for every player a choice of branch for every node they are assigned to. Okay, so in this case, for example, player 1 has 2 nodes, so we have to. So a strategy for player 1 is going to be a choice between branch 1, 2, 3 in the first node and 1, 2, 3 in the second node, and likewise for player 2. And we can also say what is a move in this game. So a move, as I said, is a branch, but if we look at the whole tree is to be a single game, then a move in this game is going to be a path from the root to a leaf. And using the type of moves that we can define inductively again, we can specify what is the payoff function of this game, which is simply a function that assigns to every path the payoff vector that we find at the end of that path. So once we have these definitions in place, we can define the translation. So this is defined inductively, and this is going to be in 2 steps. So the first step is to translate an extensive form tree into an arena. It describes the mechanics of the game. And we see that a leaf is basically going to go to a trivial game, while a node is a bit more complex. In reality, like the only interesting bit is the one in the invisible box, which tells us that a player is going to decide on a move given by the set of moves that node has, and this choice of a move is directly going to be played. So there's like a trivial play function, and a utility coming from the future of the game will just be passed on to the player. Then we have this, we have like the inductive part of this diagram, which is just like the rest of the game. So this represents the subtree that is attached at that node. And we have on top, we have this regroup reparameterization, which identifies the player which is playing now with the same player which is in the future. So this is going just to be a permutation of wires, which allows us to keep track of the strategy profile type. Okay, so nothing really meaningful. And finally, once we have this arena built, we can equip it with a product of our maxes, which represent our players and the fact they are optimizing their own payouts. So something happened in extensive from game, which is there's no way. Sorry, the extensive from games I've shown you for now are called a perfect information because every player can observe the node they're at. Okay, so they know exactly what is the state of the game when they play, but it's not true in practice. So if I play a game of cards, it is not the case that I know exactly the state of the game at every moment because players are hiding information. My opponent is hiding information from me. So I know just partially the state of the game. So we tried to also model imperfect information games, and we succeeded. And the way imperfect information is modeled in extensive for games is using this additional decoration on trees, which are called information sets. So these dashed lines link different nodes that a player cannot distinguish. Okay, so here we see that player 2 cannot distinguish between the two nodes is assigned to, and player 1's the same. Okay. So what happens is that perfect information is just a limit case of this, in which there are no dashed lines, or every dashed line just goes from a node to itself. Therefore, like information sets are just singletons. So the way that information set modify the way the game is played is through this constraint. So now players cannot just choose any move nodes of the same information set, but have to coordinate in a sense. So if I have player 1, for example, which is playing at both those two nodes he is assigned to, which are linked to an information set, then player 1 cannot distinguish between the states. So his strategy has to be the same at this point. So it has to make the same move. So on the left, we have non-admissible strategy for player 1 because it looks like it can distinguish between the first state and the fourth state at the end. But on the right, we have a correct strategy profile for both players. So you see how this information set like a long range correlation, which in some way enforces, like shows that players really put a burden on the mechanic of the game. So you cannot just ignore them. So to do so, we're going to promote our definition of extensive from game to definition of imperfect information extensive from tree, which is very similar, except as you might notice, like we replaced the decoration with players and moves with a simpler decoration with just a label I, which represents an information set. So we took the perspective of saying, okay, let's not tie different nodes and like put information set after, but we construct the tree by assigning every node to a certain information set as we define it. Okay, in this way, we can still inductively work on an imperfect information extensive from tree. So what happens is that then moves are decided by this function that to each information set, so each label assigns which moves are available, so that the construction of the tree is constrained to respect the constraint that information set put on the available strategies and moves. And there's a map we call belongs, which tells you exactly which information sets belong to which players. So we can keep track of players again. And now we can translate from this kind of data structure to open games with agency by passing through the previous translation that I've shown you. So we define first this function that takes an imperfect information tree and in a sense forgets there is an imperfect information tree. So we convert it by saying, well, a node which is assigned to information set I is going to be a node which is assigned to the player which owns this information set and it's going to have a set of moves which is given by the function n, which chooses a set of moves for each information set, and so on. So the tree that we get is the same, except we don't see any information set anymore. We can now translate this to an arena. And the problem is now we get a game which doesn't remember that some strategies have to actually be the same in different points of the game. So once we have this, we have to apply a time reparameterization, which we call clone here, that is going to say, well, at different point of the game, you actually have to copy the strategy and only get one possible play. So to have an example to look at, this is Prisoner's Dilemma, which is described by this imperfect information extensive form tree. This is a very simple game, which two prisoners have to decide whether to cooperate between them and don't spill the beans to the police, or defect and tell everything to the police. And the thing is that if they defect, they're getting like a discount on the condemn. Otherwise, they're getting the full thing. And we see that this information set here is enforcing two to not know what one did. So this effectively mimics a situation which the two players are playing concurrent. So this is the translation that we get by applying the algorithm I've shown you before. As you see, there's like this utility function which represents these leaves, and the two strategy sets are basically just fed directly to it. And we see this clone reparameterization, which is enforcing prisoner to play the same move into this in the 2 points in which they play. Okay. And what's interesting is that this can be simplified using topological moves and equations in, say, the monoidal category sets, so that actually we can get a much simpler game, which is this, which is the usual representation that we find in the literature of the open game of the Prisoner's Dilemma. And so this brings me to the end. So we've seen how to translate open games with agency, extensive for games to open games with agency, and how this is essentially, we can only do this if we model agency explicitly, and if we have a choice operator that allows us to reproduce the tree structure of the extensive form. And there are many future directions to explore. First of all, like the situation that happened with Prisoner's Dilemma, which we start with a very complex diagram that we get by direct translation, but this can be simplified, is very interesting, and it gives us an idea. Can we actually use this to discern where causal structure in extensive form games is actually there, or is just a figment of the way we constructed the game? And can we use simply topological moves to like show that some things are actually happening in parallel? And another very important direction that we ought to study is sub-imperfect equilibrium, which is a notion of equilibrium which is different from Nash's, which is explicitly tied to the causal structure of the game, and which we still can't exactly pinpoint in our framework. Moreover, open games with agency are a new framework which is tied to open cybernetics system. So there are still a lot of open question marks here and there. For example, we don't know exactly how selection functions interact with arenas. So if you note the talk, I kept the two things separated. So we first like compose the arena, and then we put selection function on top. And so it's interesting to study whether, for example, if I say every player is going to play argmax, so the preference of every player is optimize whatever numerical payoff you're giving me. Does this simplify the situation? Can I actually treat this mathematically so they can just compose arenas and forget about having to add players later? And more things that I think we don't have the time to talk now. So thanks for your attention, and this is it.
Thanks, Matteo. So I'll get questions. If you're online, you can raise your hand using the reactions, and in person, I'll ask the local organizers if they have any questions there. I'll start with Constantine online. Go ahead. You're muted if you.
Hello.
Hey, we can hear you now. Thanks.
Right. Thanks. So fantastic talk. Thank you. I was wondering if you have any ideas on how to model cooperative game theory.
Oh, that's a very good question, actually. And we have some ideas. We don't have yet a ready thing. But one of the ideas is to just like implement cooperation as an extra move and use this reparameterization degree of freedom to model the decision making that happens among players. They can decide to cooperate, then aggregate their own payoff and distribute it. And so to model in this game, in this way, what's usually called the imputation in cooperative games. And there's another interesting direction, which is we've seen like this para construction in the other talk, and we are also using that. And it seems that para is modeling the addition of a boundary in a system which delimits what's system, what's arena, and what's agents. And so can we iterate this to model hierarchies in agents? So if I have an additional level of parameterization, can I model a coalition of players which make decisions and then redirect these decisions to the single players? And like, can we model this dynamic in this way? It's still an open question, but we're definitely thinking about it.
So does this kind of change the form of the what do you call that, the ket, the resources?
I don't understand.
The payout, the payoff matrix, is that what is changing with the coalitions?
It's changing both. It's changing what, well, actually, you could say the payoffs remain fixed. It changes how they are redistributed among agents. And the way agents like have access to other agents now. Instead of being isolated, you can say, well, you can talk with each other and like decide that you can share what you get from the game. So we add like an extra layer of dynamics to the game, in a sense.
So I'm interested in the situation where the corporation kind of enriches or grows the payoff. So it's in the self-interest of the players to cooperate because that kind of grows the pie. So instead of dividing the pie, we cooperate to grow the pie, so everybody gets more.
Yeah. So this is related to this last direction that I was showing. Oh, can you go back one slide? Back. So like, the question is there some kind of assignment of argmaxes to arenas hides this question of, so what happens when I have two arenas that compose them, have two players, and normally these two players or like set of agents would compete now. But can I have some sort of like structure that tells you that, well, actually these two set of players can cooperate and get a single, form a single coalition in which they maximize the common utility. So this is something we're actively thinking about. Yes.
Okay, thank you.
Thanks, great questions.
I have a question from Matt Insall online.
Yes. So when you mentioned imperfect information games, it made me think of a game that I think is imperfect information, but it's normally modeled with probability and trees, and that is the Monty Hall problem and related games. Can you explain what you might have thought of or not thought of, or that you might think this you could do with your approach to look at that game or related or variants of it? Thank you.
So you can definitely represent it. I think here the translation is going to be really useful because it's probably easier to represent it in extensive form and then translate it to an open game if you really want to. And then like what I talked about today is the like deterministic context of games. So everything I've shown you now is diagrams in set, and there's no like probability involved, but you can of course extend this, and there's a paper by Jules and John Bolt about like doing sort of stochastic games, so in which play can be a stochastic function and in which players can have mixed strategies. So they can say, I'll play with probability X this and with probability 1 minus X this other thing. And at that point, you reach like a presentation in which you have all the facilities to actually analyze the game and say, well, okay, maybe this is more convenient than this other choice, I think. Let me know if I answer your question or.
Were there any questions in person there?
Oh, the unmute came through kind of late. I'm sorry. Part of what I'm headed for here in the Monty Hall problem is if you split the player into, say, let me give a sort of concrete example. Husband-wife team that are supposed to try to win, but after the host shows the first of the two members of the team a goat, I hope that everyone understands the version of the game I'm talking about. So the player that makes the first choice is playing outside the information or playing alone, and then the player making the second choice is brought in without the information that was provided at the beginning of the game. And the second player doesn't know, I'm not sure how to explain it, but the second player, how do you determine whether it's better for the second player to switch or not? Whenever switch means choose a different door than the original, when they don't have any information about the original choice.
So yeah, so the first
that's
player,
imperfect information, right? So, or if you think of it as one player against the host, then that player is forgetful and they forget what they chose at the beginning.
Yeah, that's definitely an imperfect situation, an imperfect information situation. And I mean, beyond representing it with an open game, I'm not sure I can give you more insight at the moment.
Okay. It's just that the usual conclusion is that it's better to switch. But how do you say what's better in this situation where the player is forgetful? They aren't able to keep up with all the information.
Yeah, I mean, what you can say is that the strategy of switching is on average better than the strategy of not switching, I think. Okay. Yeah, like this thing of like splitting the players in two might be an interesting variation for sure.
Okay, thank you.
Thanks.
All right, we better get ready to get on to the next talk. So I'll ask everybody to unmute and then thank the speaker. Thanks.
Thank you.
All right, so our next speaker is Riess from University of Pennsylvania, speaking about network sheaves valued in categories of adjunctions and their Laplacians.
Thank you for having me. Today I'm going to talk about work that I have done with Paige, Randall North, and Robert Ghrist. And we are all currently at the University of Pennsylvania. So I'm going to first start off with sort of a crash course, if you will, in cellular sheaf theory. And the theory of cellular sheaves depends really on this perspective, which says that you can associate to a very nice space, such as a cell complex, or in this talk, we're only going to talk about graphs. So let's say we have a space X, and we have a poset of face relations P sub X, describing how various cells are glued together. So it's a fact that if D is a complete category, what we would call our target category, then the category of sheaves over a certain topological space called the Alexandrov topology over our face relation poset is equivalent to simply the category of functors from our face relation poset into our category D. So in fact, when we study these kinds of functors, we are actually studying sheaf theory. So this is something I wanted to clarify before I keep going. So a cellular sheaf is simply a functor from this face relation poset. So it consists of, in the case of a graph, vertices and edges, and a vertice is less than or equal to an edge if it bounds the vertex, the edge. So like I said, in this talk, we're interested in graphs, and we're also interested in a category D that consists of categories and adjunctions. So we assign categories to vertices, categories to edges, and for any vertex that is including into an edge, we assign an adjunction between the respective categories. And really the goal for us, since we can't do so much more in general, is to compute limits of these cellular sheaves or these functors. And these limits, from kind of a systems perspective, they correspond to consistent assignments of data. So they consist of objects over all these categories, such that when we apply whatever we choose, but let's say when we apply left adjoints, that we have consistency in some sense. So that's what a global section is. And here, maybe the best way to visualize a global section is via a non-example. So in this case, we have, the real numbers living above vertices and edges. And we have this map multiplied by 1 or multiplied by -1. So we can see that this situation is twisted, and in fact, there are no global sections. So we can't assign data to all the vertices such that when we multiply it by -1, we agree over edges. So this is sort of the conceptual hierarchy of the talk, and really like my research program thus far, is that, and I say adjunctions in quotation marks because I am sort of motivated by Hilbert spaces and cellular sheaves that take values in that category. And via Hodge theory, you can define Laplacian via the linear adjunctions of maps, the maps that go from vertices to edges in our cellular sheaves. But so what I try to do, and Paige and Rob, is categorify all this. And so first we categorify this to this category of lattices and Galois connections. So it's a very simple categorification. And then, so I'll talk about that first, and then I'll talk about a categorification to this 2 category of categories and adjunctions. And then finally, I'll talk about the categorification to categories enriched over ordered monoids and adjunctions. And in each case, we have, a corresponding Laplacian, a notion of smoothing assignments of data so that things become more consistent in our system as a whole. So here is our graph Laplacian, which is really the simplest version of a sheaf valued in Hilbert spaces. Everything is one-dimensional. And effectively what's going on is we assign values to each vertex, and we have an update rule that averages values in a neighbor. And unfortunately, I wasn't able to finish rendering this animation, but what was supposed to happen is that over time, all these balls, the color changed so that they all eventually had the same color that kind of averages all the colors. And explicitly, and I won't really spend any time on this, but the graph Laplacian is given by this matrix that is given by a weighted graph, and it has all these nice properties. For example, the dimension of the kernel of the Laplacian corresponds to the number of connected components of the graph. And in fact, there's a notion of dynamics, that's driven by this Laplacian. For example, if we consider a signal, as an engineer would say, or just a tuple of real numbers associated to every vertex, we have these dynamics that eventually drives the system to consensus, where every vertex has the same value. So what I try to do is generalize all this to lattices, where by a lattice, I probably don't need to say this in this conference, but is a partially ordered set with limits and co-limits. And I just really assume everything's are complete lattices. So here we have a network where we have lattices living above all the vertices, and not pictured are lattices living above edges. So we can construct a Laplacian, and here's kind of how we do it. We start with a functor from the face relation poset over the graph to this category of lattices and connections. So this category explicitly has objects that are complete lattices, and a map between two objects is a Galois connection or an adjunction. And of course, we can compose adjunctions by composing the left adjoints and then reverse composing the right adjoints in the usual way. But something I'm kind of sweeping under the rug here is that this category of lattices and connections isn't complete because we have things going both ways. So we kind of have to make a choice, and here I choose right adjoints. So this is this category soup of lattices and join preserving maps, because every left adjoint preserves co-limits, and co-limits are joins or least upper bounds. So the intuition behind this Laplacian, it's an order preserving map between the product of all these lattices living above our graph, the vertices of the graph. It's an endomorphism. And what we do is we take all these assignments of data over vertices, and we push them to their co-bounding edges. And we do that with all the edges. And then we take the meat of things that live above edges, and then we pull back everything with our right adjoints to pull them back to the vertex V. And we take the meat of everything that we do over vertices. So this is what happens. And the really interesting thing is that we can compute the limit or the global sections consistence assignments of data via a fixed point theory of this operator L, which we call the Tarski Laplacian. And the idea of the proof is very simple. All we do is apply the usual rules we have with adjunctions. So we make use of the unit and the co-unit, and it's a really, I don't have time to show it, but it's a very easy and beautiful short little proof. And so this theorem here, that post L, where post is all the things such that when we hit it with L, we're greater than or equal to X. it really mimics the Hodge theorem, at least in degree 0, which says that, the degree 0 cohomology of something, which are, equivalent to the global sections in some sheaf theoretic, way, is isomorphic to the kernel of the Laplacian. And as a corollary, if we apply the Tarski fixed point theorem, which states that in order preserving endomorphism on a complete lattice, the fixed points of that are also a complete lattice, then we've shown that, this limit is in fact a complete lattice. So that's kind of a roundabout way of showing that. And as many of you are interested in applications, we're working on using this for graph signal processing. So instead of thinking about Euclidean data living above a graph that we want to process, we can think about data that is lattice valued. And other applications that are in the works are a distributed version of formal concept analysis, and also of course consensus, because this applying the Laplacian over and over again, iterating the Laplacian, the Tarski Laplacian, will eventually lead to consensus in the system. So the next sort of throng of my talk is cellular stacks, which are kind of I kind of think of them as they're categories living above vertices and edges instead of just lattices, which of course a lattice is a pre-order with that's complete and co-complete, but in general we can think of other categories. Maybe they're not small and we don't worry about that, but and our definition is pretty much the same, except we replace these meets with products, and we get this notion of a Laplacian. And here we have a fixed point theorem that is a little more restrictive. So we require that we consider our post-fixed points, or our suffix points, are a collection of objects and maps from that object into the Laplacian, such that this diagram commutes. And these maps here, the eta comes from the unit of this functor delta that we've defined, which this thing is just sort of, you don't mix adjacent terms, you just expand things. So you take something over here and you apply this this monad coming from here. And then, so we call this thing a cellular stack, and our theorem is that instead of them being equal, there's an equivalence of categories between the limit of the stack and the post fixed points here. And then sort of the last thing I'd like to cover is cellular M stacks. And here we assume M is a closed monoidal thin category whose unit is the terminal object. And examples include just the two-element Boolean algebra, in which case we recover the lattice theoretic perspective, because B-enriched categories are just preorders. But we also have these other options like the unit interval, where we get sort of a fuzzy notion of a Laplacian, or H could be a Hating algebra, or we can get Lever metric spaces from L. And that's sort of why I drew these blobs, because I always think of metric spaces as blobs. So we have a sheaf where we have metric spaces, for example, living above vertices and edges, and we have adjunctions between them. And we get a third Laplacian, but this is I call a weighted Laplacian, because we apply this weighting to edges of the graph. So this more corresponds to things that people actually use, where our graphs are weighted. And our Laplacian is given by this big product, but it's a weighted product, in the sense of enriched category theory. So that is sort of our definition. And this theorem that Paige proved is that, given hum of x to lx, so, these are, instead of just being, either a map, or not, this is an element of M, because remember, we're enriched in M. So in the case that, M equals 1 and M, the bold M is B, this is the same as the theorem for lattices. So this gives us sort of a control of how close we want to be to being a fixed point. And then this gives us control to how close we want to be a global section or consistency. And of course, these brackets, they mean this is the exponential object, because we assumed that bold M was closed. And so, here is our paper. And I guess I have a little bit more time. I misread my watch, but this is the paper that Rob and I wrote, and a preprint to be determined, with Paige and Rob. And I guess I should just spend the rest of the time, answering questions, if that's okay.
Thanks, Hans. Questions from in-person audience or online? I have a question. So you're talking about sort of generalizing to monoidal categories where the M is thin, like a poset. Have you thought about there could be applications when the sort of more general monoidal categories and adjunctions between them?
I haven't thought about that, but I think that is a really nice thought. Yeah, I don't know if you've thought about that, Paige. I think Paige is in the audience somewhere.
Okay, I have a question from Constantine.
Right. So I was wondering, is there some kind of positive definiteness results with these Laplacians? That's how I tend to think of Laplacians, as positive definite stuff.
Good question.
I mean, I guess like the you would like some kind of semi-group time evolution result in your fixed point.
Yeah.
So I kind of see these things as kind of heat.
Right, exactly. That's something I probably should have said, but I didn't say that. These are all, at least the Tarski Laplacian. Let me go back to that slide. We've studied the heat equation, with this Laplacian extensively, so if you impose some kind of finite condition, so you say, okay, all the lattices living above vertices and edges satisfy the descending chain condition, then in fact you can iterate the Laplacian, and you will obtain a global section, in a finite number of iterations, something like that. So yeah, in that sense, I guess when you say positive definite, there isn't a good notion of eigenvalues here. But if you restrict to some specific examples, for example, let's say our lattices
you
could
wouldn't
be
necessarily want them to be like matrices here, but kind of expressing the Laplacian as a product of something times its adjoint.
yes. So there isn't, you know, a notion of I mean, our notion of adjoint that we're playing with here is, you know, the notion of a categorical adjoint. And so in that sense, that the Laplacian is not positive semi-definite, this Laplacian L, because we could not write it as you know, the composition of a right and a left adjoint of some, you know, order preserving map. That is definitely not. Well, I don't believe that is true, but that is a good question. Yeah.
Okay, thank you.
So there's a question from Valeria in the chat. What are the hypotheses you need on the post that you're enriching over?
Okay. For the M Laplacian.
Yeah, at the end.
Okay, so we need a closed monoidal thin category. Okay, so closed multiplication has a right adjoint. Thin is that the Hom sets have at most one element, and whose unit is terminal. So the unit of the monoid is the terminal object of the category.
Hi, we have another question in the lecture theatre from Matteo.
Hi. So my question is, do you have interpretations for like what the Laplacian, what the shift cohomology, what the Laplacian spectrum is in different choices of M? Like what do you recover? Do you recover known concepts or is this new?
Yeah, that's a good question. I would say this is all work in progress that we're sharing, but that is certainly what we are working on right now, is specifically exploring these different cases of you know, a fuzzy version of this Laplacian, you know, an intuitionistic version, and then like a metric space version. And of course, you know, I and L are you know, equivalent, but their interpretations are different.
Thank you.
All right, we better move on to the next speaker. There's actually one more question in the chat, Hans. Maybe you could answer that directly. I just want to go to the next speaker though. So I'm just going to ask everybody to unmute and thank Hans. Thanks.
Thanks, Joe.
Next speaker is Jérémy Koenig, talking about grounding game semantics and categorical algebra. If you can share your screen. Great, looks good.
Good, cool.
Yeah, and go ahead.
Is my audio coming out clearly?
Yeah, I can hear it okay.
Great. Yeah, so I'm gonna present some work on game semantics and algebraic effects and how you can connect them. Those are topics in the semantics of programming languages. And since the math is not that complicated, I thought I could start by talking a little bit about the context of this work and the formal verification of computer programs and systems. Then I'll give some quick background on game semantics and algebraic effects, present my results, and explain sort of the direction that my work is taking. So building reliable computer systems is difficult because in a modern system, you have layers upon layers of complicated hardware and software components, it adds up to millions of lines of code. And if you have a bug in any one of these components, the overall system could not work as expected. And beyond that, even if your components are individually correct, it may be that their interaction brings up subtle ways to break things. For example, if they make assumptions about each other that doesn't quite line up. So there are ways to address this issue. For starters, you can think very carefully and document a specification for each component. You can make sure you carefully and systematically test everything, and there's industry best practices that tell you how to automate this, how to set up your software development process to catch bugs early, and so on and so forth. But sort of the gold standard is to actually do a formal verification of your programs and prove mathematically that your code is correct and implements a formalized version of its specification. So to prove a program correct in this way, you have to first give a mathematical semantics to your programming language so that you can actually talk about the mathematical meaning of your program and describe its execution in a formal setting. Then you have to make your specification mathematically precise. And now you can write a mathematical proof that your program is correct. And ideally, you'll want to do that in a proof assistant so the computer can check your proof, because proofs about programs are not very deep mathematically, but they're often very, very large and very intricate. And so it's hard to do that on a pen and paper basis. So, and a proof assistant can also help you to scale up this methodology to cover very large systems. And another advantage is that a third party can independently check your proof. So if you want to hire me to write a correct program to a mathematical specification that you've given me, if I give you the program together with a computer checkable proof, you don't have to trust me. You can just have your computer check the proof by itself. So over the past 10, 15 years, these sort of methodologies of program verification have become more and more tractable. There's now verified processor design, verified compilers, operating system kernels, network protocols, and so on and so forth. And there's good industrial strength tools to use to verify programs with program logics and so on and so forth. However, the next step would be to go beyond that and to have end-to-end verification of computer systems, because until then, you can still have bugs that sneak into the gaps between these supposedly verified components. For example, if you give me a verified compiler and a verified microprocessor design, but they don't agree on the definition of the machine language that the compiler is supposed to emit and the processor is supposed to execute, the combined system could still be broken. So the solution to this is to use specifications of verified components as interfaces between them, so that when two half specifications sort of match, you can compose not only the components themselves, but also their proofs of correctness together. And the main challenge with that approach is that if you want to verify a processor design or a network protocol, you're going to be using vastly different mathematical models to do that. And that's not just a historical accident, it's because verification is hard, and so you'll want to tailor your mathematical theories to the verification problem at hand to make your job as easy as possible. But that means if you have a collection of components that have been developed independently, it's usually very very hard to combine their proofs of correctness without a lot more work. So to me, what this suggests is that you can't really come up with a universal model and proof techniques that everybody should use, because that's not realistic. But you can imagine having a hierarchy of increasingly general models, verifying individual components still in specialized models, but then embedding these models in more general ones, where you could then interface these components together. So that's sort of what brings me to category theory, because it's a wonderful tool to look at existing models and try to characterize them in a unified framework, look at what they have in common, how they relate to each other, and guide the design of more general models. And so in the paper that I'm presenting today, I made a very small step in this direction, and I looked at the connections between these two lines of work. On one hand, game semantics, which interprets programs as strategies in a game that's derived from their types, and algebraic effects, which is a more sort of circumscribed and limited approach to modeling computations with side effects by interpreting these, looking at these effects as an algebraic theory and representing the computations as terms in that theory. So specifically, I will show that we can define a simple notion of strategy as in game semantics, but that can be used to build interesting models of algebraic effects. And going in the other direction, we can use the categorical tools that are used in algebraic effects to characterize this simple notion of strategy. And I hope this can be the starting points to extend this correspondence in the future and give a more solid and systematic foundation to a variety of game semantics type models. All right, so before I present my results, I'm gonna say just a little bit about exactly what is game semantics and what are algebraic effects. So game semantics is a general approach to giving mathematical semantics to programming languages. The core idea is that the types involved in a programming language are going to be interpreted as games between a component of this type and its environment. So we have a two-player game. And then programs of a given types are going to be interpreted as strategies for the component in this two-player game. And I should say that in game semantics, we focus more on the structure of the interaction between the two players and less about payoffs and winnings and equilibria and things like that. Now, game semantics has been used to give nice semantics to lots of very complicated programming language features. But from my point of view, it's also very compelling to attack this problem of verifying large-scale heterogeneous systems by assembling certified components. The reason is that games provide a very general notion of interface between components. So I was talking about network protocols and microprocessors before. You can imagine a game that consists in sending and receiving packets over the network, or you can imagine a game that consists in like accessing memory cells and doing things like that, as a microprocessor does. And so it's all just a question of setting up the right kind of moves in your games and defining the right rules. But that's one way we could hope to bridge the gap between these like various levels of abstractions involved in a complicated computer system. Now, there are challenges to overcome before we can do that. One is that there's a huge variety of constructions of games and strategies that have been used in game semantics to tackle different language and programming language features and so on and so forth. And it's not always clear why the design choices are made in this way or that way. And it's not always clear in advance what the consequences of exactly how you set up your games are going to be. So unlike algebraic effects, it doesn't have a very nice and systematic framework where we can analyze and compare different game models. Game models are often very complex, and so it's difficult to formalize them in a proof assistant, which is essential for the kind of applications I'm looking at. And finally, existing work is more like traditional programming language semantics and focuses less on specification, refinement, verifications, things like that. Now, on the other hand, algebraic effect is almost the mirror image of that. So it's a more restricted, it has a narrower scope of just being a twist on the usual monadic approach to computational effects that's used in programming language semantics, where the available side effects are given by an algebraic theory. So then the monad associated with this algebraic theory can be plugged into more traditional approaches to programming language semantics. The terms in this theory are going to represent computations. So each operation is going to represent an effect. And then the arguments of this operation are going to be the ways in which the computation could continue after the effect has been triggered. And so the computation is going to be proceeding inward and sort of trace a path within the term in that kind of way. You're going to have variable substitution is going to correspond to sequential composition of computations and so on and so forth. So the advantages is that composing effect theories is easier than in the traditional monadic approach because monads are difficult to complicated to compose. It gives you a simple and systematic framework grounded in categorical algebra. So all of the tools of universal algebra are immediately available to reason about your computations, like equational theories, blah, blah, blah. On the other hand, like I said, it has narrower scope than game semantics, and equational theories are much less general than games without restrictions. So this being said, the algebraic signatures can be read as a very simple kind of game. So I'm going to show this with an example. Here we have a simple program that has 3 different side effects. Read bit is just going to read 1 bit of information from the environment, and it's going to return 0 or 1. We have this print effect that outputs a string, and then the stop effect that interrupts the computation. So to interpret this program that says hi or hello, depending on the bit that we've read, in the framework of algebraic effects, we can define the signature. Read bit is going to be of arity 2, because there's going to be 2 potential ways to continue the computation. Print is going to be of arity 1, because it's going to do its thing and then continue without, with only a trivial outcome. And done is going to be of arity 0, because the computation is going to stop there. So the program above can then be interpreted as this term. You'll notice that print is a whole family of operations, 1 for each string, which is why it looks weird like that. But basically, you can draw this term as a tree, and then you can make the connection with the strategy tree for a game, right? So read, bit, print, and stop are going to be moves of the component. And then the counter move of the environment is going to be to choose between one of the branches of the computation and to choose how to continue the computation. So formalizing this intuition a little bit, we can have a notion of effect signature, which is a set of operation together with this arity that's going to assign a arity set to each operation. We can build a set of terms on a signature of this kind. And on a more game theoretic note, we can build a set of plays within a signature like that, and that's going to be our game interpretation. So as other speakers have mentioned, when you have a signature, you can turn it into an endofunctor. When you have an endofunctor, you can have a notion of algebra, which is going to be an interpretation of the signature on a carrier set A. And there's an adjunction between the category of algebras and the category of sets. And that's going to allow us to build a free algebra on a given set of variables X. So it turns out that in the strategy model that I've defined for FX signatures, pretty much the same story holds, but this time in the category of directed complete partial orders. And so that's a nice way to look at some of the underlying structures in game semantics and nice insights. So very quickly, because I'm reaching the end of my time, strategies can be defined through a coherence relation that are going to tell us when two plays are compatible so that they don't prescribe conflicting actions for the system. And then we can represent strategies as prefix closed sets of plays that are pairwise coherent. This notion of strategies constitute a directed complete partial order with the empty strategy as the least element. And when you do this union of strategy sets, if you have a directed set of strategies, that's going to preserve the prefix closure and the coherence condition. And so it turns out you can characterize this construction as a free algebra in this category of DCPOs, just by using this small tweak on the endofunctor, where you're going to add this lifting operation that's going to add a bottom element somewhere that corresponds to the points where you can cut your plays and form prefixes. So we can summarize this in this way. And based on this characterization, we can actually exhibit an alternative construction where we're just going to do the order completion of the set of terms in set. And that's going to be very interesting for formalization in a proof of system because terms are very easy to define as an inductive type. So this sort of alternative characterization gives you a very nice method to formalize game semantics in a proof of system. So in conclusion, algebraic effects and game semantics have a lot of themes in common, but they look at these themes of interaction and system and environment in very different ways. And so I hope that building on this correspondence I've presented, we can sort of rub these things together and try to transfer intuition between them and get nice insights about both algebraic effects and game semantics. And two small examples of this that I can give is that one way you could extend this is generalize signatures to multi-sorted signatures, which allow you to encode more complicated games. And also in the other direction, it turns out effect signatures, as I've presented them, and natural transformations between them form a symmetric monoidal closed categories that looks a lot like some of the structures that you have in game semantics. And in particular, this free monad construction can be internalized at the level of signatures themselves, which gives you things like the bang modality of linear logic that's used in game semantics, things like that. So there's lots of interesting work to be done, and I'm very excited about it. And that's what I have. Thank you for listening. And I have like 5 seconds for questions, I believe.
Thanks, Jérémy. Have time for 1 or 2 questions, maybe. Question from Paul. Go ahead, Paul.
So, okay, sorry, I'm just trying to unmute here, and I can't get the video to go off for some reason. Sorry. Thanks for the nice talk. I wondered if you, or maybe it's kind of a question stroke suggestion, whether you thought about non-deterministic strategies at all, because I had a paper with Nathan Bowler and Gordon Plotkin, which was looking at non-deterministic strategies as in terms of initial algebras and final co-algebras, but we weren't looking at DCPOs. So it might be that there will be something interesting to say by kind of combining those, but maybe I don't know, it's just a question. Have you considered anything non-deterministic?
So absolutely. And in fact, the work I've presented here comes from earlier work that I did on non-determinism in this kind of simple game semantics. And there I constructed my strategies as the free, completely distributive lattice on the set of plays. And what that gives you is a notion of dual non-determinism, so that you can have both choices of non-deterministic choices of the system and the environment, and things work very well. So the work I've presented today sort of came out of my effort to understand this model more categorically, and I'd be very interested in looking at your paper. If you can send that in the chat or send me.
Okay, thanks. That's great. I'll definitely do that if I am able.
Matt, you had a question as well?
So thank you for a very nice talk. So Jérémy, have you thought about going back to the original kinds of questions you asked at the beginning, how your approach can be applied in the following kinds of settings: fault tolerant computing for distributed systems, and the use of vector clocks and temporal logic, and the reasoning systems for addressing, again, fault tolerance in distributed systems? Thank you.
So the answer is no, I have not thought about these specific things, but if you have ideas about that, I would be very happy to hear them. What I have thought about is sort of, I have worked on the CompCert compiler and more low-level sequential things. And then some colleagues of mine are working on concurrency and things like that. So I'm sure we would be interested in your thoughts on that topic if you want to share them. But I'm sorry, I can't give a more satisfying answer.
Is there anything else you want to say, Matt? There, Matt? All right, let's thank Jérémy again. I'm just going to ask everybody to unmute. Thanks. Jérémy?
Jeffrey,
Oh, sorry.
you muted me and I couldn't unmute. Sorry. But thank you for your answer, Jérémy. I'll talk to you offline, I guess, since we're out of time. But very nice. I didn't get to clap, but there you go.
Thank you.
Yeah, I would like to ask some more questions later.
That sounds good. Feel free to get in touch with me.
Sure. I'll send you my email.
Yeah. The paper has my email as well. So
oh, great.
Just look it up on the website. I think it does. I'll write it in the chat.
All right, thanks. That's the end of the session. And we have the poster session starting in half an hour from now. See you all then.
Hi, Jeff. I can see that you're still there.
Yep.
I don't know if Jérémy is still there. Is he? Hi, Jérémy.
I am still here. Yes.
Oh, cool. Excellent. Because sorry, let me talk to you personally then. So yeah, no, very interesting. I love the talk. I particularly like this. I mean, I'm particularly worried about this business of people verifying small blocks, but not verifying how things are put together. So that was really kind of cool. And I think I am particularly interested on the idea of dealing with of these effects using stuff like what Reggie was doing. So I have some work on that, on using systems like linear logic, actually like Ritter's POM set logic, because there you have this triangle, which is non-commutative, and kind of you think about that as being sequential. And it's also based on Reggie's ideas. So I kind of wondered what exactly you're going to try to do with the, I mean, I think that the worry that one has is whether the algebraic effects are good enough for this, for the full stuff that we need to deal with or not. And if not, how you're thinking of dealing with that.
So I will say, you know, even if they're not good enough for the full thing, they can still provide a intermediate model with very nice properties on the way to embedding into more general models that can support like concurrency, things like that, and very complicated features. So either way, it's interesting. But as it relates to this before operator of linear logic that shows up in the coherent space model, right?
Yeah.
It turns out in the traditional way of doing algebraic effects, you're always going to construct the free monad right away, right? And if you stay at the level of endofunctors associated with the signature, you can actually define this free monad construction on the signatures themselves, and that gives you the dagger monad.
Okay, that's good. But are we sure that all the speakers are already? I don't quite see the list of people, but do you think yeah, looks like all right, okay. All right, then yeah, let's start then. So welcome to the poster session of this year's ACT. We have a fantastic series of posters in this session, and it is my very pleasure to introduce these excellent posters. We can have a time for one quick question and answer after each presentation, but we are also hoping that you can take advantage of the reception and the breaks after this to discuss the posters further. So now let me introduce the first presentation by Owen Lynch from Utrecht University on graphical semantic modeling with semagrams.jl.
All right. Hello. I just have 2 minutes, so I can't really explain anything, but I hope I can intrigue you. What I have here is a software that I call Semagrams. As you can see, it runs in the context of a Julia notebook, and it allows you to graphically edit semantic models. So here, I am graphically editing a Petri net. And right here, this is the famous Lotka-Volterra Petri net. And let's say I want to add like an enzyme to this. Well, I add a new species, and then I add an input here, and then I add an output here. And the pull of semigrams is that this is all very generic. Any sort of combinatorial structure that breaks down in terms of boxes, wires, and ports, which you can see on the website. There's a demo on the website that you can play with, and for the demo, it's directed port graphs. So you can add ports and add wires between the ports. And when this is running in a Jupyter notebook, you can get the combinatorial data from whatever you've just drawn and manipulate it in Julia. And that's pretty much it. That's all I wanted to show. Thank you.
Yeah, thank you. Great. Is there any question? Okay, comment that it's really interesting. So can I ask a question? A quick question. How general can this be? Because there's a category theory behind, and what sort of a general categorical framework can you manage?
So any Kopri sheaf that has where the objects in the schema are in 3 parts. So one part is boxes, which have no arrows coming out of them. The second part is ports, which have 1 arrow from going into a box. And the third part is wires, which have 2 arrows, which go to either boxes or ports. And there's a large class of Kopri sheaves that are interesting and useful in computing that fall into this category. And then we're also planning to expand this a little bit. But you just have to tell it, this is in your Kopri sheaf schema, this is a box, this is a port, this is a wire, and all of the and it'll automatically enable you to edit it graphically.
I see. Okay, great, thank you. Then let's go to the next speaker, Abel Sagodi from Norwegian University of Science and Technology, talking about conceptualizing explanations through category theory. Abel?
Hi.
Yeah, do we have slides? Okay, good.
So good afternoon. I will be shortly introducing a possible application of category theory in philosophy of science, for which we will be using categories as a representation of logical space, with which we can construct a structure for explanations for the deductive knowledgeable framework. And for this, we can represent the target exponent phenomenon, of which we focus as in which we represent the behavior of the target system showing some temporal process in a category of Conley-Morris graphs with as Morris prisms, the identity maps, which basically summarizes the behavior of a certain system. And as the exponents, which are the possible models to explain a certain temporal process, we will use the category of local flows with the as objects local flows over a suitable space for the target system, and as morphisms topological equivalence. And we can construct a functor from the category of local flows to the category of Conley-Morris graphs by sending a local flow to the finest Conley-Morris graph of its maximally invariant set. And this will then allow us to say that an explanation for a phenomenon Y with hypothesized models A will have an explanation if f applied on A intersected with y will be a non-empty set. And finally, in a construction with topological conjugacy as the morphisms in the category of local flows, we can identify predictions of the effects of bifurcations, which will be the interventions in the mechanistic framework of explanation. Thank you.
Okay, great, thank you. Yeah, great. Is there any question from the audience? If not, can I ask you a question? So is this a sort of a one example taken in mechanics/dynamics, or because deductive nomological model cannot be applied to various sorts of things? And it seems that, so do you have any sort of a general formalization, categorical formalization of DN model behind this?
No, so this would only work for some kind of temporal process that we consider.
Okay. No. Oh,
Not
that's
for laws or other possible targets. That one. Okay.
Oh, and also there's a question by Valeria, but I think for this, sorry, I took the time for myself. So can we go to the next presentation? My apologies. So the next presentation is by Henry Kvenge of Pacific Northwest National Lab on Sheaves as a framework for understanding and interpreting model fit. Henry?
Great, thank you. Can you hear me?
Yes.
Awesome. Okay, so I'll give a really short summary of sort of what's in this poster. So this arose out of some real world problems related to studying gene expression for some complicated data sets. So the underlying pitch here is that in data science, we deal with really large, complicated data sets that often have lots of metadata associated aside from labels and attributes and properties and things like that. And yet, at least most commonly for data scientists, we still think of these things as being just sets with no additional structure. So our idea was to try to impose some additional relations among data points in a data set in order to better understand model performance. So this is a big problem that's starting to emerge within machine learning, where it's become clear that focusing completely on global statistics, such as the total accuracy on a data set, can lead to big problems down the line when you find out that your model is actually, failing catastrophically on certain subpopulations. So basically what we lay out in our paper is a way to create a finite topology on a data set based on metadata, labels, things like that. And then the question is, how do you want to store things like the models itself, statistics about how the model fits on different subpopulations? And we basically take introduce two structures: a data sheaf, which is just a sheaf in the most boring way possible, and then another structure we call the model pre-sheaf. And essentially, we look at how models do well locally versus globally on certain subpopulations versus other subpopulations based on whether the process of modeling, how much the process of modeling deviates from being a pre-sheaf morphism. So that's a very, very quick summary.
Fantastic. Yeah, thank you so much. Is there any question from the audience?
Yeah. Yes, Ahmed.
Yeah, we have a question here.
Yeah.
Hey, hi. So my question is, what's the role of the sheaf condition here? I see the data sheaf is a sheaf, but the model per sheaf is not a sheaf, right?
Yeah, that's right. So the data sheaf, and unfortunately can't really go into the actual details that you might want, but the data sheaf is a sheaf in sort of the most boring way. So you're really just taking the points that comprise a certain subpopulation and assigning the raw data to them. So for example, in the case where maybe you're measuring sensors or something, and you have a collection of sensors that are sort of related that form an open set, then the data sheaf would just be the values you measure at those sections. A section of that sheaf at that open set would just be the data that you're measuring on those sensors. So obviously you can do all the gluing and everything you'd need to do trivially, no interesting structure. The interesting structure is how that deviates when you actually start to try to model things. And in general, that will almost never be a pre-sheaf morphism, and the model pre-sheaf I mentioned will almost never be a sheaf.
Okay, thanks.
Okay, thank you. So let's say, so the next speaker is Mark Addis from LSE on syntax, semantics, and formalization of social science theories. Mark?
Thank you. Since I've only got 2 minutes, and this is a previously published paper, what I'd like to do is to highlight some of the key general conceptual points, and then encourage you to read the paper. The paper is essentially an application of the institutional theory, model theory of Gorgon and Birstall to formalizing social science theories. The essential idea of Gorgon and Birstall's institution theory is to be able to provide a fully abstract definition of model theory. And in that sense, it represents an extension and going beyond the original abstract model theory of Lindstrom and Bauweiss to a fully categorical representation of model theory. In institutional model theory, there are fully abstract definitions of syntax, semantics, and satisfaction. Now, what that enables you to do is to model different theoretical vocabularies as vocabularies for various signatures over an institution. Crucially, you have what's known as the duality of the Galois connection, which relates the closure conditions of a set of sentences to the closure conditions of a set of models and gives you a generalized condition for semantic and syntactic equivalence. When you have that, you can use that basis to develop an algebraic scientific theory calculus, which is rather like an interpolation calculus. Now, the benefits of this are that it enables you to have a new perspective on syntactic approaches to scientific theories, and in particular, to provide strong formal evidence that the debate between the semantic and the syntactic approach to scientific theories is, in point of fact, not really debate at all, because they can be seen to be interchangeable. It also has the additional benefit that you can use it as a flexible framework to model social science theories if you have an underlying structure and a degree of theoretical variation. So it's got applications more widely outside the philosophy of science.
Okay, great. Thank you so much. Is there any question from the audience?
I have a question. Yeah. So can you give us an example of a particular social science theory, a particular institution that would illustrate your ideas nicely?
Well, the example I give in the paper is the formal learning theory developed by Kevin Kelly, essentially where you've got formal learning theory developed over recursive relations in sets. And that's one possibility. But you can also do it with anything, for example, say social science theories that are probabilistic, where you've got sufficiently similar underlying logical structures, because what it allows you to do is preserve truth under change of notation.
Okay, thanks very much.
Okay, great. So the next speaker is Matteo Spadetto from the University of Leeds on the Gödel vibration. Matteo?
I'm here.
Okay, good.
Can I start?
Yeah. Go ahead.
Thank you so much for the possibility of presenting the Gödel vibration, which is a joint work together with Davide Trotta and Valeria De Paiva. I'll start by saying that Valeria in her PhD thesis introduced the notion of dialectica construction associated to a Lex category in order to internalize Gödel's dialectica interpretation of high-things arithmetic. Then Hyland and Beering generalized this notion to an arbitrary vibration, and Hofstra showed this construction to be actually the composition of two completions, the simple sum completion and the simple product completion, which are called sum and prod respectively. Taking advantage of this presentation, we asked ourselves, When is it the case that a fibration is the dialectical completion of some fibration P prime? And in this case, how is P prime made? In order to answer, we studied the monads, sum and prod, and we introduced some notions like the following. The notion of being free from the existential quantifier. We say that a predicate in a fiber of a fibration is free from the existential quantifier. Let's call it alpha, when any proof of a statement of the form there exists B such that beta from alpha factors through the canonical proof from beta of G for a unique term G. Then you can give a similar characterization of universal quantifier free predicates. And you say that a Gödel fibration, this is our notion, is a fibration with a simple products, a simple coproducts, enough of these existential quantifier free predicates, in such a way that the full subfibration made of them has enough universal quantifier free objects. Okay, let me just say our main result, and then I'm done. It says that a fibration is actually a dialectical completion precisely when it is a Gödel fibration. And in this case, the fibration that you needed to complete, to dialectica complete in order to get the fibration that you started from, is the one made of the universal quantifier free predicates inside the subfibration of the existential quantifier free ones inside the fibration that you started from.
Okay, great. I think for the sake of time, let's but thank you so much. Let's go to the next presentation. So it's a Tim Hosgood from Topos Institute on Dirichlet polynomials and entropy.
Hi. Yes, so this is a joint work with David Spivak. So let's go quickly. What is a Dirichlet polynomial? This is if you look in the box with a 1 in it. What's a Dirichlet polynomial? It's a thing of this form. It's like a polynomial, but you switch around your exponents and the other things, you know? So rather than y to the n, it's n to the y. So you have this with natural number coefficients. We write y because you can think of this as the Oneda embedding of finite sets, and that's all really nice. This is very familiar if you've seen any kind of polynomial functor stuff. It's just kind of dual to that. And you get this cool thing, you get kind of like a Dirac delta function for free, which is slightly interesting. Won't talk about it. Why do we care about Dirichlet polynomials? One reason we care about them is they are equivalent to bundles of sets. So this is something already written out in a paper by David and David. And the two bits that tend to be important of your Dirichlet polynomial when you draw the corresponding bundle are d of 0 and d of 1, which we have nice formulas for. And when you look at this picture in number 2, you can see how this bundle kind of looks like it's describing a probabilistic scenario. We've got 5 outcomes and we've got 8 draws or 8 choices to make. 4 of them lead to the first outcome, the other 4 all lead to the other 4. So this is a picture of 4 to the y plus 4. So that the leftmost column is the 4 to the y, then you've got 4 copies of 1. And then we can forget that story completely and talk about something else. We can find a rig whose underlying set is the non-negative reals times the non-negative reals. And we define its multiplication pointwise, but in its addition, we kind of add the first component and in the second component, take the weighted geometric mean. This gives us a rig. We call it the rectangle rig. There is a rig homomorphism from the rig of Dirichlet polynomials to the rectangle rig, where we just send n to the y to nn. We call the first component the area, the second component the width. We have a nice corollary that tells us there are combinatorial interpretations of these numbers. Then kind of the big pizzazz of the paper is you can define Shannon entropy in the kind of usual way. We define this thing called length, which is normally called the perplexity. And it turns out that these two numbers you get from the rig homomorphism, area and width, are such that length times width is equal to area, which is true for rectangles. So that's good. That's my time.
Okay, great. Thank you so much. Is there any question from the audience?
I will just, sorry, there is a link to the archive paper. I've put it in the chat. I forgot to put it on the poster.
Oh, okay, okay. Any question?
So I have a quick question. So for traditional polynomials, there's a notion of polynomial functor, right? Which is interesting. I know that David Spivak is a big fan of those. So I guess you are as well. Is there like an analogous polynomial functor scheme in the Dirichlet model?
This is something that David can answer if he's here, but I'm not as into polynomials as David is. So that's something he would answer. I'm afraid.
Is he here? Maybe I don't know. Maybe he's not.
He is here, but I think he's
keeping.
I am here. Yeah. 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 I mean, the Dirichlet maps over D0 from D to D are also the polynomial maps from D to D. The only reason we chose Dirichlet rather than poly is that the kind of Fritz, Baez, Leinster stuff of subtract, like where you push forward along something, makes more sense in the Dirichlet setting than the polynomial setting.
Okay, thanks a lot.
Okay, great. So the next speaker is Daniel Lockhart from Ben Gurion University on norms on categories.
Okay. Yeah, thank you very much. So I'm presenting joint, the clock isn't ticking. Okay, so I'm presenting a joint work with Matt Insel, who you already know from many questions today. So what we were trying to do is we want to generalize the concept of a norm from something on a vector space to something on a category. Well, actually, that's not a new idea at all. So actually, it goes back to Levere. But our motivation came mainly from the fact that we wanted to find a more systematic way to do concrete metrization, like for pointed metric measure spaces. And so what is new in our approach are these now axioms N3 and N4. They basically say, okay, if I have this norm on a morphism and it goes in both, vanishes in both, there's a morphism with vanishing norm in both directions, then both objects are isomorphic with respect to the norm, and then there's a kind of compatibility axiom in the N4, and basically we can apply it to the case of metric spaces, where we can show that we can build a metric that is almost recovers the classical Gromov-Hausdorff metric. But it has also many other interesting applications, like you can see there for normed vector spaces. And we actually want to continue this approach and try to prove actual theorems in this setup, like a theorem going back to Freudenthal and Turjewicz, or the Kantorowicz-Rubinstein theorem, and generalize that to even more complicated norms, because so far we restricted ourselves to basically compact objects to get to satisfy these axioms. Thank you.
Okay, great. Thank you so much. Any question? Okay, if not, yeah, can I ask one? So you said that the you can in the usual, so you can almost recover the usual norm in the Hausdorff.
Distance. Okay. Yes. Yeah. It's in the middle column at the bottom. So yeah. So it's if you take the identity map with one metric on the other side, the Gromov-Hausdorff metric and our metric, then the map is two Lipschitz in one direction, but only Cauchy continuous in the other direction. So if it were Cauchy Lipschitz continuous as well in the other direction, then you could say in any reasonable sense that it's basically the same, but it's not, a little bit less.
Okay, interesting. Yeah, thank you so much. Okay, so let's get to the next speaker, Elena Di Lavore from Tallinn University of Technology on Dialectica Petri nets.
And good afternoon, everyone. I am Elena Di Lavore, and I'm going to present Dialectica Petri nets. This is joint work with Vilmer Liel and Valeria de Paiva. Our main goal is to have a model of Petri nets that allow us to compose them using linear logic connectives. We also want to be able to talk about different kinds of Petri nets. So this is why we used one of the Dialectica categories that has the linear logic structure and also allows us to change the kind of arcs in the Petri nets. In the category that we used, Petri nets are the objects, and morphisms between them come from morphisms in the Dialectica category, and they represent simulations between Petri nets. In fact, as you can see on the top right, the net below can simulate the one above. As I was saying, these Petri nets are closed under linear logic connectives. So we can take products, coproducts, monoidal products, and internal homes of them. The other interesting feature of our nets is that we can change the kind of arcs between places and transitions by just changing one parameter of the construction. For example, we can talk about arcs that are uncertain by endowing the 3-element set with linear structure. And similarly, we can talk about arcs with probabilities or model the role of inhibitor substances in chemical reactions. And finally, we can take products of lineals and specify, for example, both the rate at which a substance is consumed in a chemical reaction and whether the substance is a reagent, an inhibitor, or a catalyst. There is still much more work to be done. We would like to be able to model notions of behaviors of nets, like the token game. We would also like to investigate whether we can extend our framework to differential linear logic. And finally, we would like to know whether it is possible to code our nets, for example, in CADLab. Thank you.
Okay, yes, great. Thank you so much. Any question from the audience?
I have a question.
Yeah,
have you looked at categories of executions of these kinds of nets and how the arcs bearing additional meaning act on the structure of the categories of executions?
So as I was saying, we haven't looked at behaviors of these nets. So like the token game and that kind of things we haven't looked at yet. But,
oh, okay, thanks.
Yeah. Thank you.
Okay, there are more questions, but they are, so yeah, I hope you're going to use the reception and breaks, but let's get to the next talk by Jonas Frey from Carnegie Mellon on elementary 1-2 cosmoses and labeled linear logic. Jonas?
Hello, can you hear me?
Yes.
Thank you. So the work I'm presenting today originated in discussions about the notion of elementary 1-2 topos. But today I will be using the term 1-2 cosmos rather than 1-2 topos. To start, recall that an elementary 1 topos can be defined as a category with finite limits, such that for all objects A, the presheaf of internal relations into A is representable. The representing object should then be viewed as a power object of A. We categorify this as follows. Definition. A 1-2 cosmos is a poset-enriched category with finite limits such that for all objects A, the presheafs of internal posetal profunctor into and from A are representable. Note that compared to 1 toposes, the representability condition splits into 2 since profunctors are not symmetric. The representing objects are then a kind of lower and upper power objects of A. Besides being a categorification of the notion of 1 topos, this is also a decategorification of Street's notion of elementary cosmos, which is cat-enriched rather than poset-enriched. As an important difference to toposes, the monadicity argument used to show that elementary toposes have finite co-limits fails in the 1-2 cosmos case. The algebras for the directed double power object monad are the completely distributive lattices, which are not necessarily atomic, in contrast to completely distributive Boolean algebras. For every 1-2 cosmos E, there's a virtual double category prof E, whose vertical one cells are the morphisms of E, and whose horizontal one cells are the profunctors. As internal language for this virtual double category, we can use a kind of tagged linear logic with substitutions. For example, the sequent on the right expresses the existence of a 2-cell in the left rectangle. Using this calculus, we can show that the virtual double category prof E is closed and has compositions. Furthermore, the posets of profunctors into and from the terminal object are Heiting algebras. Thanks for your attention.
Great, thank you so much. Question from the audience?
So I have a question. So could you just summarize again the relationship between the term topos and the term cosmos? You recall the definition of topos, but then you don't use the word topos again. You said something at the beginning about topos versus cosmos, but maybe I'm a bit confused about that.
Yeah, so the definition is a categorification of this definition of topos, as I stated it. But then you cannot prove, you don't have this monadicity principle, so you cannot prove finite colimits. And so that's not a full definition of what a 1-2 topos should be. For a 1-2 topos, you should add some conditions to have some more colimits. But it's, well, we observed then that it's very close to what Street called a cosmos. So in a cosmos, strictly speaking, Street had to add some size conditions because it matters to be a maximization of pre-sheaves in a certain sense. But in the posit-enriched case, you don't need the size conditions. And so that's where this notion comes from.
Okay, thank you.
Okay, great. So the final speaker of the session is Josh Tan from the University of Oxford on the type system of digital institutions. Josh?
Yep. Hi, everyone. Thanks for having me here. So today I'll be presenting some work in progress with Alexander Petrov, who's at ETH. First off, I should be clear, the institutions that we talk about here are definitely not the institutions of abstract model theory, so don't get those things confused. Though I think it's maybe some interesting connections. We'll see. Just contact me later, Mark. Anyways, so a bit of background about this paper. This research really emerged from a very practical question, which is basically a group of collaborators and I are working on a project called Metagov, which among other things is a software framework that connects and integrates a bunch of other digital services used typically by platforms like Facebook, Slack, or Discord. Now, these are services like voting, identity, reputation, etc., that typically communicate through low-level protocols such as APIs. And what we wanted is, because we work with a bunch of these different sort of component services, we really wanted a way of organizing and connecting those services. So separately, I've been working with Jules, Philip, and other people kind of in the open games community to use open games to model generic social institutions. And the idea of this paper is kind of take this to the next step, where we directly, we model these social institutions which exist online. These institutions are actually already sort of digital components. So we're just mapping the endpoints, the API, the low-level API endpoints of these services to an actual open game. And then the plan is to use that open game as a kind of interface for building these platforms. So basically the idea is summarized in the slide there. And the main difficulty that we've encountered so far, roughly speaking, since this is kind of like a project in the scope of like, how do we actually apply open games in practice, is that in order to build this open game and then sort of effectively build an effective mapping, we first actually need to build a standard that unifies all these different software and what they're doing, which is actually like quite hard. Anyways, so this is work in progress, and hopefully we'll be able to report more in the coming months.
Okay, that's fantastic. Yeah, thank you so much. So any question from the audience? If not,
I have.
Okay, go ahead.
Sorry, it's Jamie. It's me again. I have a question.
Yeah, sure.
So I really like this idea, Josh. Could you could you sort of sketch a sort of example end goal? So you give an example of digital institutions, Facebook, these sort of complex online systems. What would be a possible output when this project reached fruition? I'm imagining something like you would encode the framework of the digital institution, and then the system maybe would tell you whether or not the system is going to reward truthfulness of the participants, or it's going to lead to a framework where there's positive dialogue rather than I don't know, YouTube comment channels where it's just sort of hate piled upon hate. I don't know, is that the sort of, you're trying to unpick and predict social dynamics in that sort of way? Is that right? Or maybe I've got the wrong idea.
That's exactly what we're trying to produce. Though I think the emphasis of the research project is more on producing like data set to support that analysis. So like what I think of as like a library of essentially like open games that had like pre-built kind of like have some pre-built queries or like think like social unit tests that support like checking of these like conclusions. And then when people actually like build these services, because the underlying sort of stuff is going to be almost always more complicated. There's UI elements attached. There's a lot of technical details that gets abstracted. But we can then say, if you build it in this way and make these connections and these parameter choices, you are going to get like a bad outcome or a good outcome, or based on the sort of pre-performed game theory analytics.
Thank you. Really interesting. Thanks very much.
Okay, great. So I think this is the session. So it was a really fantastic session. So let's thank the speakers with a. Okay, so after this, I suppose there's a reception scheduled. I don't know how it works. So
so I'm afraid the reception. I'm afraid the reception is just for the people in Cambridge. Sorry, Kohei.
Okay. Oh no. I was
expecting a glass of. If you're expecting a glass of champagne to be arriving at your door, sorry about that.
Well, it's still morning here, so I was not thinking of drinking. But yeah.
Isn't that a breach of contract?
I don't know. I'm not. I'm not currently. I'm not. Yeah.
Well, you
my
guys
university doesn't buy me. Yes.
Well, you guys can have your own reception here. We're going to have our reception in the sun, drinking wine, if that's all right. But thanks again, everyone, and Kohei for a great session. Thank you.
So does that mean you'll leave on the Zoom so that we can talk?
Yeah, absolutely.
Yeah, that'll be great. That'll be great. Yes.
Yep,
That's absolutely fantastic.
I can get my own. I can get a beer or something and sit here and chat.
Okay, lovely. Yes.
Jorge and Elena, you're talking about interesting things, and I was starting to write a response in the chat. If you're still with us, then maybe we can talk a little bit more about these reactions that are self-catalyzing.
Oh, yeah, thank you.
Yeah, Jorge, do you mean, so I would expect that a self-catalyzing reaction would be one that, and it's been a long time since I looked at this terminology, but would be one that, because of one of several possible conditions, can doesn't need a separate catalyst. So for example, having a higher quantity of the reactants